All right, I want to very briefly just talk about something known as diagonalization. That's a pretty big, long word and hard to say, but it's a very useful thing, and try and explain a little bit of that to you from the textbook, which is section 5.2. Now, we first start with a definition of what we call similarity. So if A and B are, again, two square matrices, such that there exists a square matrix of the same size, P, that's invertible, and this relationship holds. B is equal to the inverse of P times AP, P inverse AP, right? In that case, we say B is similar to A. That's a definition. B is similar to A if there exists some invertible matrix P such that P inverse AP is equal to B. Now, first thing to say is that if B is similar to A, then A is similar to B. So how does that work? If B is similar to A, we have this, but if A is similar to B, there must be some matrix where A is equal to the inverse of that matrix, B times that matrix. Well, it's pretty easy to see what that is. If we start with this, that B is similar to A right here, what I'm going to do is I'm going to multiply both sides of this equation by the matrix P on the left. So PB, reminds me of peanut butter and jelly. Sounds good. PB times, or equals what? P times this stuff. Now this stuff I'll regroup, right? The P inverse becomes the identity, and I'm just left with AB. So PB equals AP. Now I'm going to multiply on this equation on the right by P inverse. P inverse here, P inverse here. Right? So here I'm going to manipulate this. P inverse becomes the identity, and I just get A. So A is equal to P, B, P inverse. Well, if I choose Q to be P inverse, then the inverse of Q, which is the inverse of P, is just P. And I get Q inverse BQ, which is the form I need it to be in to say A is similar to B. Okay. So, I don't know if you followed all that. That was a little bit of a switch-swatch, flip-flop, or whatever you want to call it. But it is true then that if A is similar to B, then B is similar to A. So we can talk about them. They come in pairs. Okay, they are similar to one another. All right. Now, what does it mean that they're similar? Why do we define this idea, and why do we call it similar? In what way are they similar? I mean, because if I just take this matrix P and its inverse and multiply A in this way, I fail to see how those will be similar. Well, there are many properties that they hold that are similar. For starters, we'll show that they have the same determinant. So if A and B are similar to one another, then this relationship holds, right? Where P is invertible. And what I want to do is take the determinant of each side. Right? Since these matrices are equal, their determinants are the same. Okay? But over here, then, the determinant of a product of matrices, again, go back to your remembrance of what we did with determinants in Chapter 2. The determinant of a product is indeed the product of the determinants. Right. And remember, at this stage now, here, right inside here, P inverse AP, I can't rearrange the order I multiply matrices in. Remember, matrix multiplication is not commutative. So P inverse AP is not just P inverse PA. Some of you might be saying, why can't we just write that as P inverse PA and then B is equal to A? No, you can't do that, right? But now, when I've taken the determinants, right? Determinants are what? Real numbers. This is the product of three real numbers. I can rearrange these any way I want. Also, some of you remember something about the determinant of P inverse. What is that? Remember, that's 1 divided by what? The determinant of P. And if I go ahead and swap the order here, just so we can see it very clearly. All right, these are all real numbers. What do we know about these two quantities? If we multiply them together, we get 1, right? And 1 times the determinant of A is the determinant of A. And there's the proof, right, that determinant of B is equal to the determinant of A. And so similar matrices share many properties. Sometimes these are referred to as similarity invariants. The two matrices have. And so let me just show you a summary of some of those properties from the book in section 5.2. And this is on page 303 in the book. And here are the similarity and variance here. We've already shown that they have the same determinant, right? Two matrices that are similar, A and B equal to P inverse AP, they have the same determinant. And of course that means what? That they share invertibility. If A is invertible, then B is invertible, because they have the same determinants, right? And they're both invertible if what? The determinant's not equal to 0. They also have the same rank. They also have the same nullity. Remember, rank is what? The dimension of the row space or column space. Nullity is the dimension of the null space. They have the same trace, which is kind of interesting. Easy to find the trace, but they do have the same trace. They have the same characteristic polynomial. Hey, that's talking about eigenvalues, and therefore what? They have the same eigenvalues. Now, does that mean they have the same eigenspaces corresponding to those eigenvalues? Well, no. If lambda is an eigenvalue of A, then it's also an eigenvalue to P inverse AP. The eigenspace of A corresponding to lambda and the eigenspace of P inverse AP corresponding to lambda have the same dimension. So they have the same dimensions, not necessarily that they are exactly the same vector space. Okay. So similarity is very nice in a lot of ways. In particular, if I can get my matrix that is similar to a matrix where it's easy to find all these things, right, and other things, then I can use that fact to transfer these corresponding values to my matrix, right, since they're the same. And what type of matrix is it easy to find other than the zero matrix, right? What's a matrix, a non-zero matrix that's easy to find all these things? Well, one is a diagonal matrix, And so let's talk about that. If I can find a diagonal matrix that my matrix is similar to, that is a good thing. And so a square matrix is said to be diagonalizable. Well, I can't even say that. Diagonalizable if it is similar to a diagonal matrix D. Which means what? There's an invertible matrix P such that P inverse AP is equal to D, where D is diagonal. Okay? So we're going to talk about how do we determine that, and more importantly, how do we find the the matrix P in that case. To diagonalize, we say diagonalize our matrix. Well, I'm not going to prove these theorems, but I do want to state them and then talk about the results that we find in the proof of one of these theorems. But if A is an n by n matrix, then the following are equivalent. A is diagonalizable if and only if A has n linearly independent eigenvectors. So there's one condition. If A has n linearly independent eigenvectors, then A is diagonalizable. So the question is, we find this process, diagonalizable means they're similar to a diagonal matrix. Is every matrix diagonalizable? No. But ones that have n linearly independent eigenvectors, they are. So when we say n linearly independent eigenvectors, we know that for a given matrix here, n, we could have up to n different eigenvalues, and each one has corresponding eigenvectors. Right? So if we throw them all together, all those eigenvectors together, let's say it this way, the basis vectors for the corresponding eigenspaces, if there are n of them that are linearly independent, then A is diagonalizable. Another theorem which we can look at is if we have k, right, here's k, distinct eigenvalues for the matrix A, so they're distinct, right, they're not all the same. And they can be the same, for instance, we were talking about the algebraic multiplicity in the last video. So if you have a an eigenvalue of algebraic multiplicity 2, it's sort of a repeating root, if you will, and you can have the same eigenvalue. So if we have k distinct eigenvalues and the corresponding eigenvectors to those eigenvalues are v1 through vk, then that set of vectors forms a linearly independent set, which is important here because, right, not only do we have to have n eigenvectors, they have to be linearly independent. And so this theorem says an n by n matrix with n distinct eigenvalues is diagonalizable. Right? Because if there's n distinct eigenvalues, then this theorem says that they're linearly independent. And then this theorem says, right, that therefore we're diagonalizable. All right, so in the proofs of these theorems, there develops a method for diagonalizing, and it's in page 305 in the book, and I want to take a look at that. And it sort of summarizes, if you will, in a way, these theorems and what we've been talking about here. So the process. So here's the procedure. It's on page 305. So, first we're going to determine if the matrix is actually diagonalizable. And we're going to search for n linearly independent eigenvectors as we were looking at those theorems. So one way to do this is to find a basis for each eigenspace and count the total number of vectors obtained. If there's a total of n vectors, then the matrix is diagonalizable. If the total is less than n, then it's not. Okay, so it's just it. So basically we just do the eigenvalue problem that we did in the last video. We find all the corresponding eigenvalues and eigenvectors, find a basis basically for the eigenspace for those eigenvectors. Take all those vectors. If there are less than n, then the matrix will not be diagonalizable. If there are n of them, then it is. And so if you've ascertained that the matrix is diagonalizable, we're going to take those n vectors and we're going to slide them in as columns of the matrix P. We're going to create the matrix P from the columns, from the eigenvectors by taking those eigenvectors and sliding them in as columns of P. And that's the P that we need to diagonalize the matrix A. P inverse AP will be a diagonal matrix. And because it's diagonal, if you remember, the eigenvalues for any triangular matrix, diagonal matrix in particular, then will appear in the main diagonal. If you remember that. We looked at that in the couple videos ago. So these eigenvalues will appear along the main diagonal in the diagonal matrix. So this is from the book example. This is we'll do one as well, but here's the book's example. And I think this was the 3x3 matrix we found the eigenvalues and corresponding eigenspace for in my video previously. Here's the characteristic equation. You see the eigenvalues are 1 and 2. For lambda equal 2, these are the two basis eigenvectors, right? These two vectors here. And for lambda equal 1, this is the basis vector. Notice this is dimension 2 vector space. This is dimension 1 for the corresponding eigenspaces. But what we do is we just take these vectors and we slide them in. You see that? We're just sliding them in into the columns for the matrix P. That's my matrix P now. And so as a check, I can multiply P inverse is this matrix. Here's the matrix A. Here's P. P inverse AP multiplied together gives me this. It is indeed diagonal, and notice down the main diagonal, what do we have? The eigenvalues. Now 2 is repeated twice, and again, that's because it's a multiplicity 2, algebraic multiplicity 2, so it's going to appear twice. Okay, and then there's the eigenvalue of 1. Now, do we have to slide these eigenvectors, these basis vectors for our eigenspace, do we have to slide them in this order? No. I mean, I can change the order that I put them in. If you change the order, all that does is just change the order that these eigenvalues appear along the main diagonal. It'll either be 2, 2, 1, or 1, 2, 2, or 2, 1, 2, and so on. So that's the only effect. Okay, so there's no preferred order for that at all. Let's take a look at this example here. So this matrix here, from our notes before, so from the previous video, we showed, right, on eigenvalues and eigenvectors, so that would be eigenvalues and eigenvectors part 2 video, I think. We said for lambda equals -7, the basis, or a basis, was the one vector 1, 1. And for lambda equal 5, the basis was -2, 1. Okay, so this matrix is diagonalizable because it has two distinct, right? It's 2 by 2. It has two distinct eigenvalues and, of course, two corresponding basis eigenvectors, if you will. So we can find the matrix P by sliding in, right, this vector here, 1, 1, and that vector there, -2, 1. So there's the matrix P. Now, with your calculator, you could find the inverse, or if we want to, we can go back and find the inverse with that formula that we had, or we can use the inversion algorithm. We talked about that way back, but there's the inverse for the matrix P. And then I want to look at what is P inverse A times P. So you should actually do this calculation if you're doing the problem on a test or something, to make sure that indeed you get a diagonal matrix. The matrix A is up here. And the matrix P is here. Okay, so I would like you to use your calculator and just multiply these matrices in this order and make sure you indeed get the following matrix, which is diagonal. And what do you see along the main diagonal? The corresponding eigenvalues, as you should. Okay. You can confirm now the similarity properties. For instance, you can take the determinants of both of these matrices and they should be the same. We said that would be the case, right? And the determinant of this matrix is clearly what? Just the product of the main diagonal entries is -35. The determinant here is what? -3 minus 32. That's -35. Okay. The traces should be the same, right? If I add -7 and 5 together, I get -2. What's 1 plus -3? -2. Traces are the same, right? The rank, the nullity is the same, and so on. So all those similarity and variance are true here. Okay. Now, for a 2 by 2 and a 3 by 3, not a very bad ordeal to find the diagonalizing matrix P. I should say diagonalizing matrix P. But obviously it gets a little bit harder for larger size matrices. Okay. Now there's some very helpful calculations, and I'll just close with this, that you can do with diagonalization. And one is that you can find large powers of a matrix using diagonalization. So if you have a matrix A that's diagonalizable, right? So P inverse AP equals some diagonal matrix, and there's their eigenvalues right down the main diagonal, zeros everywhere else. Well, if you square both sides, right, what happens? Of course, if you square any diagonal matrix, it's easy. You just square the main diagonal entries, right, themselves. That was when we looked at the special matrices. Diagonal matrices are very nice in that sense. But if I look at this expression here, if I square P inverse AP, it's P inverse AP times P inverse AP. And look in the middle there. The P times P inverse is just the identity. A times A is A squared, right? And we get this expression. Well, if you think about that, if I cube both sides or raise it to the 4th power and so on, what's going to happen? In general, to the kth power, I get this. P inverse AKP is what? Just raising these main diagonal entries to the kth power. And I can solve for AK, right, by multiplying both sides by P on the left and P inverse on the right, and I get this. A to the K is equal to this. Now, here's the neat thing. If I want to find a large power of the matrix A to any power, then it's much easier to do these calculations. Okay, so for instance, if A is equal to this matrix, and we showed in the previous, what we talked to their example they did in the book, right, that the matrix A is diagonalizable, and it's diagonalizable by this matrix P, and P inverse AP was this, right? There's the diagonal matrix. So if I want to find A to the 13th power, right, then A to the 13th power is P d to the 13th pi times P inverse, right? P inverse. You do have to do some work to calculate those guys. But here, d to the 13th is just raise each of these to the 13th power. And that's not too bad. I mean, you have to have, especially if it's a high power, some way of computing those numbers, right? And you do have to multiply these three matrices together, which takes a little bit of time. But think about if you just computed A to the 13th power by itself. That would be, go back to this matrix A over here. That would be this matrix A times itself 13 times. You'd have to multiply 13 3x3 matrices together. And that's a lot more than just multiplying 3 matrices together. Again, you do have some little computation here, and you do have to find these diagonalizing matrices P and P inverse, but it's much quicker. Especially, as this remark, what if you wanted to do, instead of A to the 13th, A to the 1000th power? Well, that's really, really complicated on this side. This side's not bad. The only thing that changes is you now raise 2 to the 1000th, and 2 to the 1000th, and 1 to 1000. So as far as the actual matrix product, simple. Okay. So there's lots of things that can be done with this diagonalization process. Very helpful thing. So similarity and diagonalization. I want you to be able to diagonalize a 2x2 or 3x3 matrix using this procedure, and then make sure you check and confirm that it is indeed diagonal. Okay, so in the next final lecture, we are going to be looking at something called a Markov chain or Markov process, and this is a really neat application, and we'll come back to the eigenvalue problem with it. So it'll bring us full circle in this as we close out next time.